All right, so welcome to our 21st lesson of Calculus 2. So our saga continues with respect to finding all of these different types of series tests. So we know whether or not a series is going to converge or diverge. And as a repeated reminder of our motivation, remember, these are going to be useful for us later when we try to write out these infinitely long polynomials to represent functions that are exceedingly complicated as functions that are relatively simple. That's kind of our main goal, but it's really easy to forget that when we kind of get in the mire of all of these series tests here. Fortunately, the one we're going to learn today is probably the easiest one to use, other than maybe the test for divergence, because all you do for that one is take a limit. Today, we're going to learn about the alternating series test. Okay, now we've seen this word alternating before in the form of a sequence, right? So can someone remind us what an alternating sequence was? What was that? Yeah. That's right. Yeah. So when it flips between positive and negative signs every single term. That's right. So it stands to reason that an alternating series would be if we add up an alternating sequence. Now, the nice thing about alternating series is that there's a really nice test that we can use to look at them. So let me write out what an alternating series looks like in general. So we have our series, and then we have -1 to the n, and then we have times something else where this is usually supposed to be greater than or equal to 0. You can't do something silly like put another -1 to the n right here and call it alternating. So this is usually has to be positive. Now the thing is that this is what's causing the alternating. So this is going to be called our alternator. And -1 to the n is by far the most common alternator, but there will be a bunch of other alternators that we're going to see as well. So some alternators that we can use are -1 to the n. We can also use -1 to the n plus or minus 1. So if you shift it by 1, it's not going to change anything. Sometimes we'll see, what is it? Sine of pi over 2 plus pi n. So this is always going to land on an odd multiple of pi over 2, and that will always be 1 or -1. Cosine of pi n is one of them, and there are a bunch more that you can create. All you essentially need to do is you need to flip sign every single time. Now, there are some things that look like they might be alternators, but they aren't really. So these are going to be false alternators or imposters. So probably the most common one is just sine of n without any kind of modification like that. So what's wrong with that? That changes sign pretty frequently. Well, the problem with this is that it doesn't change it regularly enough for our purposes. So sometimes it'll be positive for 2 numbers in a row, or sometimes it'll be negative for 2 numbers in a row. So this one's not going to cut it. Another one that wouldn't count as an alternator would be something like -2 to the n. So even though this would flip sign every single time, it's also going to change the size of what we're looking at. So this isn't really an alternator. Although if we put it like this, then that would be okay, because then we would have an alternator times something else right here. All right. So there we go. There are alternators. So let's talk about the alternating series test. So we need an alternator times our sequence that's positive, and then we have an alternating series. And then how do we know if these converge? We use the alternating series test. And once again, 3 words are too long. So this is going to be the AST. If a sequence an greater than or equal to 0 is decreasing and the limit as n goes to infinity of an equals 0, then the alternating series, -1 to the n, a sub n, converges. And that's it. That's the whole test right there. So all you need to do is have an alternating series, make sure the part that isn't alternating is decreasing and going to 0, and then it's going to converge right here. And that's all we really need for the alternating series test here. All right, now one key thing about the alternating series test which it has in common with the test for divergence, is that it only tells us about one thing. It only tells us about convergence. You never say something diverges by the alternating series test. So that's one thing I want to emphasize here. So can't diverge by the AST here. Does that say sequence or series before A sub n? Oh, this should be sequence. There we go. All right, let's take a look at an example. And you'll see how easy this is to use. All right, so let's use the AST to determine if n equals 1 to infinity of negative 1 to the n over n converges. All right, so let's go ahead and write this as an alternating series. So we write it as the sum from 1 to infinity, negative 1 to the n, and then we have 1 over n. So this is going to be the thing we're looking at. So this is the, you can almost imagine it as like the meat of the alternating sequence, and then this is just the alternator here. So we need to see if this, which will be our an, we need to see if this is decreasing and heading to 0. All right, so let's check both of these. So is 1 over n decreasing? Is that true? Does 1 over n get smaller as n gets bigger? Yeah, that's going to be true. That's right, because we're dividing by a larger and larger number. Okay, does 1 over n go to 0 as n goes to infinity? Is that going to be true? Yes, that's right, because it's 1 over a huge number that will go to 0. All right, so since both of these are true, and this was an alternating series, then we say that this series converges by the AST. And that's it. That's all you have to do. So alternating series are really nice. And a lot of people ask me throughout this part of the course, oh, which series test do I use when? If you see an alternating series, try the alternating series test, because you can see how pretty straightforward this is to use. So why don't you guys practice this? Okay, so this time, take a look at the series n equals 1 to infinity, negative 1 to the n, e to the 1 over n minus 1. And see if this converges or diverges. So I'll give you guys a minute or two to look at that. Is that 1 over n? Yeah, that's 1 over n. All right, give you guys another few seconds here, and then we'll talk about it. All right, let's take a look at this guy. So this one is alternating as we have a negative 1 to the n. And then this is, so our an is going to be what's next to that. It's going to be e to the 1 over n minus 1. All right, well, let's apply the alternating series test. So is e to the 1 over n minus 1 decreasing? Well, this one's a little bit harder to see than the previous one. Remember, if you ever want to show that something's decreasing, one option you always have is to take the derivative of it and see if it's negative. So you could do that for this one. But another way of doing it is that we see if n is getting really large, then the exponent here is getting smaller and smaller, right? And e to a lower exponent will get smaller the lower the exponent is. So that means that this will be decreasing. So you can kind of reason it out like that if you like as well. But if it's really not obvious, then I would recommend taking a derivative. All right, the second condition, we need the limit as n goes to infinity of e to the 1 over n minus 1 equals 0. So is this going to be true? Well, let's see here. So if I send n to infinity, I'm going to get 0 as my power, right? And then e to the 0 is 1, and then 1 minus 1 will equal 0. So that will be true as well. So therefore, this series, -1 to the n, e to the 1 over n minus 1, will converge by the alternating series test. All right, wonderful. Now I want to do a very similar example, but it's going to turn out a bit differently. So this time, I want to take a look at the same series, only we're missing that -1 there. So we're just going to remove that part. All right, so I'm going to try AST. So my first condition is e to the 1 over n decreasing. Well, for the same reasoning as before with the last one, if you make your power smaller for e, you're going to get a lower number. So yeah, it's going to be decreasing. But now for the second condition, if we look at the limit as n goes to infinity of e to the 1 over n, what's that going to be this time? 1. And unless we want a degenerate mathematical system, 1 is not equal to 0. So it does not pass the alternating series test here, since we do not get 0 for our limit. Okay, now does that mean we say, oh, it just diverges by the alternating series test? Remember earlier, the alternating series test only tells us if things converge. However, there is a test that we commonly use if the alternating series test fails. What other test do you think we could use if this doesn't even head to 0? That's right. We're going to use the test for divergence. So if this doesn't head to 0 at all, well, then maybe this whole thing won't head to 0. So let's try the test for divergence now. So the test for divergence says we look at the limit as n goes to infinity of our sequence, and if we don't get 0, it diverges. All right. So let's see here. We know that this guy is heading to 1, right? We just saw that over here. So this is the limit as n goes to infinity of -1 to the n times 1. But then what's happening is that this number keeps bouncing in between -1 and 1. It just keeps slipping between a number close to 1, a number close to -1, and it's not going to settle down no matter how far we go. So this limit's not going to exist, but in particular, it's not going to be equal to 0. So what we would conclude from all of this is that this series diverges, but we would say it diverges by the test for divergence, not the alternating series test. We would say it diverges by the test for divergence here. So be careful which test you're saying you have here, because you shouldn't say it diverges by the alternating series test. All right, and that's it. That's the alternating series test in a nutshell. So you guys can go home. No, I'm just kidding. not that. One thing I want to talk about that's related to alternating series, but isn't quite the test here, is something called absolute versus conditional convergence. Now, what on earth is all of that? Well, these guys right here hinge on the idea that it's easier for an alternating series test to, or sorry, it's easier for an alternating series to converge than it is for a non-alternating series to converge. So easier for an alt series to converge than a non-alternating series. Okay, why is that? Let me address some of the questions here. Are the multiple choice options for the exam going to have us pick the right test to use? Yeah, that's very likely. Will we have to use the test for divergence if we don't meet those two conditions? That'd be an excellent thing to try. Yeah, usually if the AST doesn't work, then TFD might. So it doesn't have to go to a different number to show divergence by the TFD. Yeah, the test for divergence says that if you're not going to 0, then you're going to diverge. So like no matter what you're doing, whether you go to a different number than 0 or maybe your limit doesn't exist at all, if it's not 0, then it's going to diverge by the TFD. Okay, now let me get back to this here. It's easier for an alternating series to converge than a non-alternating series. Let's take a look at two series and see why that is. So let's say we have the sum from 1 to infinity of 1 over n, and we start looking at this. We have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, and so on. Now let's take a look at the alternating version of this that we saw earlier. -1 to the n times 1 over n. So this will be -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6, etc. Okay, now let's see here. So we're adding up all of this stuff, right? But here, what's happening is that if you look at these in pairs, like you look at these in positive and negative pairs here, you end up having them partially cancel out with one another. So rather than accumulating 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus all of that stuff, so far after going 6 terms, we've only accumulated 1/2, 1/12, and 1/30, which is going to be way less in magnitude than this is up here. So as you can see, this is accumulating less value, meaning that it's going to be more likely for this to converge than something like this, which is accumulating more value over time. And in fact, this series here, this diverges, but then this converges. So that's kind of what I'm talking about here. It's easier for an alternating series to converge in general than it is for a non-alternating series. Okay, now the difference between these two, the only difference is that we had a -1 to the n here, right? So one way we're going to view alternators, we're going to view alternators as a handicap. Because remember, it's easier for an alternating series to converge than it is for a non-alternating series. So if you take a non-alternating series, you stick an alternator in there, it's automatically going to be easier for that to converge. So here's kind of like my analogy for this. So let's say that, actually, let me proceed a little further before I talk about that. So let's see here. This is going to give us two types of convergence. So we're going to have conditional convergence, meaning that the series needed the alternator to converge. And then there's absolute convergence, meaning this series didn't need the alternator to converge. Okay, so here now I'm ready to give my analogy here. So a series that converges absolutely would be kind of like an NBA player in basketball. They're really good at the game. They can handle making a lot of shots on the standard size hoop. Now, if you gave them an alternator, if you gave that really powerful series, or the series that converges quickly, an alternator, that'd be like asking an NBA player to play basketball with one of those little 5-foot-tall Fisher-Price things. If you're good at regular basketball, you're probably also going to be pretty good at making shots in your 5-foot-tall little plastic thing. But on the other hand, let's say you're a series that converges conditionally. So let's say you're, I don't know, maybe like 6 or 7 years old or something, and you're getting pretty good at using your little Fisher-Price basketball hoop. But then you go and you try to make shots on the regular one, you're probably not going to be as successful with that. So absolute convergence is stronger condition, and it's harder for series to be absolutely convergent. All right. So another way of saying this, rather than verbally right here, is absolute convergence is where, let's see, if, sorry, I'm really confused today, sorry. Absolute convergence, a series AN is absolutely convergent if the absolute value converges as well. So how is this the same as what's going on up here? Well, putting on your absolute value onto your series, that's effectively getting rid of the handicap, because if you put an absolute value on your -1 to the n, that's going to go away. But if you were able to survive that, if you not only converged when you had your alternator and then when you got rid of it, then you're going to be absolutely convergent. Whereas conditional convergence doesn't survive such a transition. Conditional convergence is going to be if a series AN converges, but if we put those absolute values on there to make things harder, this is going to diverge. So if you get rid of that alternator, then it's not going to converge anymore. All right, now notice that both of these have convergence. Both the original series will converge no matter what, whether you're absolutely convergent or conditionally convergent. It's just kind of an extra bonus requirement. Now, if our series converges, why do we really care about this distinction? And we already have a convergent series, it's already adding up to a nice number. Why do we care about this? Well, it turns out that once we get to these infinitely long polynomials, one of the most crucial properties of those depends on the series being absolutely convergent. So in the future, conditional convergence won't be good enough. We need to have things be absolutely convergent. So it's kind of something that's, again, kind of like all these series tests, is something that we're going to be using a bit later here, but it will end up being important eventually. So it's important to know whether these are absolutely or conditional. All right, enough talking about this. I feel like I've talked a little too much here without doing an example. Let's do an example. All right. So first of all, we want to take a look at the series n equals 2 to infinity of cosine of pi n over natural log of n, and see whether it converges or diverges. All right, now if it does converge, what we're going to do this time is we're going to see whether it converges conditionally, meaning it needs an alternator, or absolutely, meaning it didn't need its alternator. You might be like, alternator, well, wait a minute, I don't see a -1 to the n in here. Well, remember, this was also an acceptable alternator. So cosine of pi n, if you plug in successive values of n, if you have cosine of any whole number multiple of n, it'll be either 1 or -1, and it flips between them every time. So this is just another way of saying -1 to the n here. All right, so in order to see if it converges or diverges, well, it's an alternating series, so why don't we try out our new alternating series test? All right, so our a sub n, the stuff times the alternator, is 1 over natural log of n right here. All right, remember there are two conditions. The first one is 1 over natural log of n decreasing? Is that going to be true? Well, let's see. If we plug in larger and larger values of n, natural log is going to keep getting bigger. So 1 over a number that's getting bigger will be getting smaller. So yes, that will be decreasing. Or we could have done the derivative of this as well. All right, and then the second part here is, does 1 over ln of n go to 0? Well, let's see here. If we look at the limit as n goes to infinity of this, well, natural log does go to infinity, albeit really slowly, but it goes to infinity as n goes to infinity. So we have 1 over something getting huge, I give us 0. Okay, so we know that this series is going to converge. We know if we add all these terms here, it's going to end up converging. Now, the thing we want to know is, will this series still converge even if it doesn't have the alternator? So now let's check for absolute versus conditional convergence. So the way we do that is we get rid of the alternator. So it's lost its handicap. It has to play basketball on a real hoop now. It has 1 over natural log of n right here. So let me ask you guys this. Is this series going to converge or is this series going to diverge? Yeah, it looks like we got some diverges here. So this is going to diverge. Now, why is that? Well, one way we could do this, so we could use a limit comparison test maybe to show this diverges, or maybe a regular comparison. But technically, this is also a piece series, because this is 1 over n to the 0 times ln of n to the 1. And remember, that fits into our generalized p-test there. And since our power of n is 0 right here, this diverges by the generalized p-test right here. All right, so there we go. So this is going to diverge. But remember, that doesn't mean the original series diverges. All that means is that the original series really needed that alternator to converge. So we say that this only converges conditionally. And in some instances, that's fine. It doesn't really matter. If they ever ask you if something converges or diverges, we could have just stopped right here, and that would have been enough. But in some instances, we really do need that absolute convergence. So that wouldn't be good enough in those situations. All right. So I'm going to repeat the same example here. So I'm going to try the same thing again. Only this time I'm going to try it with the sum from 2 to infinity of cosine of pi n over n squared. Why would we need absolute convergence? That's what I was saying earlier. For these infinitely long polynomials, there's going to be something that we want to do with them where we need absolute convergence for that. So it's essentially we're trying to prepare for that coming thing with those polynomials. All right, so this is an alternating series. So let's use the AST to see if this even converges. So our AN, the thing next to the alternator, is 1 over n squared right here. All right, well, is 1 over n squared decreasing? Well, if we make n larger, then we're making our denominator larger as well. So our overall fraction will be getting smaller. So yes, it is decreasing. Next, we check the limit. Does it go to 0? Well, that's going to be true as well, since we're making our denominator really massive here. So this is going to end up equaling 0. And then that means that this at least converges. But once again, maybe we're using this in the context I've been, forementioning here. Maybe we need to see if this converges absolutely. So this time we're going to look at it without the alternator and see what that does. And what's it going to do this time? Is this going to converge or diverge? This one's going to converge. That's right. Converges by the p-test, since we have 2 greater than 1. So the thing about this series is that it converged as it was with the alternator here, but it didn't really even need that to converge. It still would have converged anyways, even if it didn't have its alternator. Even if you slapped absolute values on there and you got rid of it, it still would have converged anyways. So that implies that the original series is absolutely convergent. Another way to remember this is absolute kind of means absolute values, meaning you can slap absolute values on your expression in here and it'll still converge no matter what. When did we go over the p-test? It was on the same day as the integral test. So I would look at your notes there. All right. Now, one final property of alternating series I want to talk about that's really nice is while we can't sum them up directly, remember I said it's really hard to know what series sum up to, even if they converge. While we can't sum them up directly, we can use we could use a result to approximate alternating series really well. We can't get exact answers very easily, but we can get approximations. Okay, so what I'm going to talk about next is called the alternating series remainder estimate. Okay, so I'm going to write out what this is symbolically, and then I'm going to explain it. So what this is this inequality. The absolute value of the nth partial sum minus the entire series, it has to be an alternating series. The difference between these, or the distance between them, has to be less than an plus 1. Okay, so what on earth does this mean here? What is this inequality saying? So the fact that it's absolute value means how far apart those two things are. And what are we seeing how far apart? We have the nth partial sum. So remember, the nth partial sum is where we stop adding terms up at whatever the capital N is. And then on the other hand, we have the true value of the series. So this is what the series is actually going to sum up to. So this is the approximation, and then this is the real value right here. Now, what this is saying is we're seeing how far apart the approximation is from the real answer. And like I said, I'll say this again, it's really hard to know what series sum up to in general. So the best we can do oftentimes is make an approximation of them. And what this is telling us is the maximum error in our approximation. So if we only want to add up to the nth term rather than adding up infinitely many terms, our error can't be more off than the next term we would have added in our partial sum. And depending on the sequence, that could be really nice. But the main thing is that we have a nice formula telling us how far away our approximation is from our real value right here. All right, let's go ahead and take a look at an example of this. I think it'll sink in a little better. All right. So what is the maximum possible error for using S3 in place of the series n equals 1 to infinity, -1 to the n over n cubed? Okay, so let's say we wanted to use S3 instead of this series here. So S3, what is that? Let's write out explicitly what that is. So we plug in n equals 1, and we have -1. We plug in n equals 2, and we have 1/8. And then we plug in n equals 3, and have -1 over 27. So that's what S3 is. And what we're proposing doing is that rather than adding up infinitely many terms, we're only just going to add up these terms right here. We're only going to add up to n is 3. Remember, this doesn't mean 3 terms. It means we go up to n equals 3. So we're using this in place of that. And at first, that might seem like a terrible idea because we're missing infinitely many terms. We're missing terms 4, 5, 6, 7, 8, 9, on and on forever. But as we'll see, it's actually not going to be that far off, even if we only use the first 3 terms here. All right, so what's the error here? Well, the difference between S3 and the true sum of the series has got to be less than 1 more than this with our A's. So remember, this was A1, A2, A3. A4 is just going to be the next number that we would have added to our running total or our partial sum. Now, one thing that's really confusing with this is that your AN does not include the alternator. So this here is AN. AN never includes the alternator for this, and it'll never be negative, because after all, you can't have a negative number being bigger than an absolute value right here. All right, so A4, what is that? That's if I plug in n equals 4 into this, that's going to be 1 over 64. So using this in place of adding together all infinitely many terms, it might be inaccurate, but it's not going to be more than 1/64th away from the true value of the series. So let me write that out to conclude. So S3 is no more than 1 over 64 away from the true sum of the entire series. And that's pretty awesome. We only added together 3 terms, and already we're getting down to single-digit percentages with error. And I think it's pretty clear here to see that if we add more terms, like maybe we looked at S4 instead, then our error would get even less. So the more terms that we add in there, the less our error, or our maximum error, is going to be. So whatever this adds up to, I don't feel like combining all those fractions, but whatever this ended up being, it's going to be no more than this far away from what the series really sums up to. All right, now I want you guys to practice this. So let's do a problem that's kind of similar. So what is the maximum possible error for using S4 in place of the series n equals 0 to infinity of -1 to the n over n factorial? All right, so why don't we check that out? Can I move it up? Oh, you mean like this? Yeah, sure. What's 0 factorial? It's 1. Yeah, that wasn't a mistake. 0 factorial actually is. Let me bring this down. There we go. Isn't 0 factorial 1? Yeah, that's right. It's kind of weird. It doesn't quite feel right, but that really is the case. Can the error be negative? No, the error won't be negative. Remember, don't include the alternator as part of your AN when you're doing the error part. Only include the stuff next to the alternator. Let's see, 1 over 120. over 24. All right, give you guys another few seconds and then we'll go over here. That'd be 1 over 4 factorial because we started at n equals 0. Remember, S4 doesn't mean 4 terms. It means we go up to n equals 4. So technically S4 would have 5 terms, as weird as that sounds, because we'd have 0, 1, 2, 3, and 4. You just need to find an plus 1. Yep, that's that's all you do. Pretty easy to find the error. All right, let's go ahead and take a look at this. So what is the maximum possible error for using S4 in place of this series right here? All right, so remember the difference between S4 and the series can be no more than the term we would have added to S4 next, which would be A5. Now in this problem, our A sub n is 1 over n factorial. It's the stuff that's next to the alternator here. So that means that A sub 5 would be 1 over 5 factorial, and 5 times 4 times 3 times 2 times 1. If you do all of that, you're going to get 120. So that means that S4, let's write out what the interpretation is. S4 is going to be A0 plus A1 plus A2 plus A3 plus A4. And S4 does include the alternator. So we would have 1 minus 1 plus 1/2 minus 1/6 plus 1 over 24. So whatever this ends up being, this is less than 1 over 120 away from this right here. So whatever this series actually adds up to, this fraction is no more than 1 over 120 away from the true sum of the series. And by using this method, you can keep increasing n to a larger number and your computer won't mind. You can effectively sum up series that we couldn't have summed up before by approximating them to any error that you would like. So for example, if you're, say, have an error tolerance of 10 decimal places, you just keep making your n bigger and adding up more terms until your error gets below 10 to the negative 10. And then that's it. Oh, question 2 asks for the mass possible difference. That's the same thing. So I'm talking about the difference or the distance between these two numbers here. So that's asking for the same thing. All right. So there we go. So we're actually going to use this a lot later to approximate the value of things that we would normally use a calculator to do. So for example, how did people in the olden days figure out what like 1 over e was? They used techniques like this, for example. All right. Well, it looks like we did get out a few minutes early anyway. So I guess I will see you guys next time when we will go over our final pair of tests.